Hi. So today in this video, we're going to talk about another theorem that we can obtain from the previous one that we discussed last time for the nested interval theorem. Okay, so this is called the Bolzano-Weierstrass theorem. Okay, so and we're going to first have a look at this theorem, and later we're going to try to prove this based on the nested interval theorem that we discussed previously. Okay, so this theorem is saying that we're going to let this xn to be a bounded sequence of some real numbers. Okay, so and then it must be that there exists a convergent subsequence of that. Okay, so we call this convergent subsequence as x and k, which is a subsequence of xn. Okay, so that's it. All right, so we're gonna have a look on this little picture. So here, just for now, just ignore those red parts. Okay, so we have this curve or this sequence. Okay, that is bounded by those two dash lines. Okay, those two black dash lines. So, and we can always find a subsequence of that original sequence to be a convergent subsequence. Okay, and for example, we have, so this must be a infinite sequence. Okay, we haven't plotted all of those, right? So we have something later after this. We can see that all those blue dots, okay, that I pointed on this sequence, we can simply put them as a subsequence. And so by the definition of the subsequence, that'll be just still some sequence, but those points are selected from the original sequence, but they still keep the same order. Okay, so now we have collected some points, those blue dots, from the black sequence, and then we still order them in the original order, and then we can see that this sequence, it has to converge to somewhere. Okay, all right, so that's the intuition of this theorem. Okay, so basically the proof of this theorem is to use the nested interval theorem, and by constructing some a lot of those closed intervals or closed sets. Okay, so we simply, here you can have a look on those red parts. Okay, so those red parts are some separations or some splits on this original space. Okay, so originally we have this the biggest set here, right? And those are the boundaries for the original sequence. Then we can simply cut, or we can split that the whole one into two, and we can divide that into two different sets, or two different closed sets. Okay, and then we focus on the other part, and that has to contain some part of those convergent subsequence. Okay, and then we can keep doing that, and then split that again and again, right? So because then we can use the nested interval theorem, right? And from the last time, we know that there has to be, so the intersection of those closed intervals, it cannot be empty, right? And we also proved last time that this intersection of those closed intervals, they must contain precisely one point. Okay, and that point will be exactly this limit of that subsequence, convergent subsequence. Okay, so this is the rough idea of this proof. Okay, so now we can have another example before we start the proof, right? So this is sort of in this kind of illustration. We can have another example where we have, let's say we have some points, okay, in the some points here, okay, and they are forming this original sequence, okay, and we can still use that method or this idea of this proof, right? So we can first, so this is a two-dimensional space. We can first cut or split that into maybe 4, okay, so we can simply divide them by those axes, right, and that gives us this part of the closed form, right? We're gonna, of course, we're gonna have some boundaries here, right, as the initial boundaries for that first closed interval, right? And then we can focus on this and have another separation on this, right? And finally, we're gonna find some point which is we're gonna find this intersection of all those closed interval, and finally, for the last one, we're gonna find that exactly the 1 point that we're gonna have for this limit of the sequence. Okay, so that's basically the idea of this proof. Okay, so now let's gonna try to show exactly the proof of this theorem. Okay, good. So first, let's recall that a real sequence. Okay, so that is just a function. Okay, this x, okay, from n and map to a real number, okay, and then we can let this xn, okay, we can define this to be x of n, right? So that's some real sequence. So the image of the sequence, okay, is the subset, okay, x of n, okay, and that'll be this set xn where n is in n, okay, and that has to be a subset of R. Okay, so that's some, so the image of the sequence is this subset, right? So if, okay, so for the first case, which is easier, so if the image xn is finite, okay, first, if the image xn is finite, okay, then there exists some real number, okay, alpha, okay, such that xn is alpha for infinitely many those n's, right? Okay, so say that for all k in some s, which is a subset of n, say infinite subset, okay? All right, then we can use the well-ordering principle. Okay, so we can exhibit the elements of this S as an increasing sequence of those natural numbers, right? Okay, have the elements of S as an increasing sequence of natural numbers. Okay, so that's from n1 less than n2 less than nk, so on and so forth, right? Then we know that the subsequence x and k is the constant sequence alpha, right? So it is convergent. Then subsequence x and k is the constant sequence alpha, so it is convergent. Okay, so that's the easy part, right? If this image is finite, right? So for the other kind of more difficult part, so let's say this xn is infinite, okay? Okay, but no worries, since we know that this xn is bounded, right? So that's also very useful. So since xn is bounded, okay, so there must exist some positive real number, okay? Let's simply say that this is r plus, okay? Where we have, so this m is positive real number such that, okay, from minus m to positive m, okay, those are the boundaries for this xn. That's by the what is given to us, right, from the starting point of this theorem. So this is bounded, right, for all n. Okay. Then we can do something as we said in the beginning, right? In those pictures, we can split or just divide the interval, okay, to some two subintervals with the same, exactly the same length, okay? So equally divide them. Divide the interval and divide the closed interval, okay? Those are very, very important. You can see that this is including those boundaries, right? Closed set. Okay, so we divide, we call this as J0, okay, defined as this closed interval, okay, into two sub-closed intervals of equal length. Okay, so the one of those will be from minus m to 0, and the other one will from 0 to m, right? Okay, all right, so then we know, because xn, okay, is a subset of this this whole, the original one, right, the whole one from minus m to m, or we can rewrite this as the union of those two separate ones, right? Okay, so it means at least one of the subintervals will contain infinitely many elements of xn, okay? So this is a very important step. At least one of the subintervals will contain, okay, infinitely many elements of this xn, okay? Why this is true, we're gonna ask ourselves, right? So let's say if no none of those subintervals contain infinitely many elements, then that violates our starting point, right? Because we said that that was a sequence and it has infinitely many points, right? So this has to be true, right? So at least some of those subintervals, maybe two of those, right? But at least one of the subintervals will contain infinitely many of those elements, of those points, right? Okay, of this, so that is infinitely many, okay, can call this points, right, or elements of the given sequence. Okay, so, all right, so that's good. Then we can work on those divided intervals, right? So we call one such subinterval as some j1. Okay, let's work on this j1. Okay, so that one has to be those that, as we mentioned, right? That has to be those one that contains infinitely many of the elements. Okay, so we select those ones. So now we work on that one, this j1. Okay, now again we can divide or split this j1 into two subintervals again, right? So we can do that. Okay, so now we can divide j1 into two subintervals, okay, of equal length again, like iteratively, right? So that's what we're doing right now. Good. So, and then we can notice that since this xn intersects j1, that is infinite, okay, by our choice of j1, right? As we just mentioned, we have to choose those j1 to have those infinitely many of those points. So one of the sub intervals of j1 must have infinite number of elements from this intersection, right? As we just mentioned. Okay, good. Then we can call that as j2. Okay, name it as j2. Good. Then we obtain the next one, right? So then from here, you can see that j2 is a subset of j1. Okay, and we know that the length of j2, that will be half length of the length of j1, right? So because we said we simply wish to have exactly half of those previous ones, right? And that'll be a quarter of the length of j0. Okay, and that'll be, let's say, so we know that this j0 has a length of 2n, right? So that's multiplied by 2n. Okay, good. All right. So, and we notice that this j2 also has infinitely many terms, okay? And those terms are collected from xn, from our original sequence. Okay, good. All right, then we do this iteratively. Okay, keep doing this. Okay, then we construct a nested sequence of intervals Jn. So going back to the picture as we mentioned. Okay, for example, in this, right? So previously we have this as J0, and then we took a half this one, right? So this one contains infinitely many of those points, and then we take half, right? So that's exactly what we're talking about. Okay, so all right, and this, okay, so now we successively constructed a nested sequence of intervals Jn with the following properties. Okay. Okay, first, so Jn plus 1, of course, is a subset of Jn, okay, for all n's. Okay. All right. And second, so the length, we have a specific length for Jn that would be exactly, let's say 2m plus 1, right? 1 over that. N times m for all n. Okay. All right. And the last property is that for each n, okay, so the interval Jn, it contains infinitely many terms of the sequence. Okay. Okay, good. All right, so then we are able to use the nested interval theorem. Okay, so now everything's ready. So using nested interval theorem as we discussed last time. Okay, so we can get a real number alpha, okay, such that alpha is an element of all those intersections for Jn's. Okay. All right, and that'll be the, and you may already know that this alpha is exactly this limit, right? But we're gonna show that later. So now, okay, so this is sort of like an algorithm, right? So it's interesting that we can see a lot of mathematical proofs there using sort of the idea of the iterative algorithms. But actually this is, algorithms are also coming from this kind of proof called the inductive proofs, right? But so this is also originated from mathematics. Good. So now we inductively define a subsequence, okay, which has a limit or which will converge to alpha. Okay, because J1 contains infinitely many terms, okay, of the sequence Xn, so there must exist some n1, let's say, okay, this n1 is such that x1 is in J1. Okay. And assume that for all I, okay, from 1 to some k, we have found x and I such that we have x and I is an element of Ji. Okay, now Jk plus 1 will contains infinitely many terms of the given sequence. So there exists nk such that nk plus 1 greater than ni for those j from 1 to for those I from 1 to k. Okay, with the property that x and k plus 1 is an element of jk plus 1. Okay, so basically that's still the thing that we have discussed, right? So after we split that, then we can then we select the one contains the infinitely many of those terms. Okay, and we keep doing this, and thus we get a subsequence x and k, right? So that's how we construct this subsequence. We just pick or we just collect all those points that we need, right? As we just mentioned here. This is just a formalization of how we are picking those points, right, to form this subsequence. Good. So, all right, and then, okay, x and k that converges to alpha as k goes to infinity. Okay. And this is because since okay, so for all right. So for x and k in Jk, as we mentioned, okay, we have x and k minus alpha. Okay, so that distance that has to be less than or equal to the length of Jk, right? So it has a maximum distance. Because that distance, it cannot exceed this maximum length of this Jk, right? Okay, and that length, we know this is 1 over 2 to the power of k. This is actually 2 minus k plus 1, right? And that goes to 0 as k goes to infinity, right? And then this completes the proof, right? So as k goes to infinity, then that x and k goes to alpha, okay? So that alpha will be exactly our limit of that subsequence. So it is convergent, right? Good. So, all right, maybe we should fix this, right? So this is not, we should have this as 2 minus n plus 1, okay? All right, good. So then from this proof, we have iteratively constructed this, a lot of nested intervals, right? Then we use this nested interval theorem to help us to find this limit of the convergent subsequence, okay? And this is given the condition that we have this original sequence that is bounded, okay, by some real numbers. Okay, Good. So this is the Bolzano-Weierstrass theorem, okay, and that's also a very useful one, and that is based on our previous result from the nested interval theorem. Okay, good. So that'll be everything for this episode.